We can start?
Yes.
Okay. All right, so let's start. Thank you very much for all being here, despite the nice weather. Now it's very beautiful again. So my name is Monika Eilsburger. That's my first lecture today out of 4. I'm a tenure-track professor at LMU in Munich since 2019. And I have worked on periodically driven lattices and artificial gauge fields already during my PhD, which I also did at LMU, and then I went for a postdoc to Jean Dalibard in Paris, and now I'm back in Munich, building a new cesium experiment. Some of you may have seen the poster. I will also show you another picture just as a teaser in case you didn't go to the poster yet. You can still have a look and ask a few more questions. And I'm also building now an ytterbium experiment which has related ideas going into the direction of gauge fields for lattice gauge theories. So the plan is to first actually talk a little bit about geometric properties and topology just to set the stage. So today there will be also a lot of classical physics just in order to, get a feeling of what geometry means and where there are systems where interesting effects may occur in the presence of non-trivial geometries. And then we'll move on to how topological systems can be engineered with ultra-cold atoms. And because most of the things that I will show you then do not really consider the experimental system anymore, and we have heard a lot about interacting photons and so on, I just want to very briefly mention again how our system looks like and what you may expect how this looks like in the lab. So this is the beautiful picture I like to show, which is from our cesium lab at a time where actually not everything was built up yet. So you actually see the various cooling stages that you have also learned in the lectures last week. So this is still one of the PhD students. Here we have an oven section where we heat up the cesium atoms. Then we have here the Siemens slower where we send in a counter-propagating laser beam in order to slow down the atoms in the first place. Then we have like a second section here, or first vacuum section here, where we laser cool the atoms. So there's a magneto-optical trap. And for cesium, there are also very efficient Raman sideband cooling techniques in optical lattices, which we use. So at this point, the temperature of the atoms is like a few microkelvin. And then we transport it over this distance of around 43 centimeter to this glass cell, which we are very proud of. So we brought a 3D model of it. So probably you have seen it already. And so this is the first stage. Then the second stage in the science cell, then we evaporate further and generate Bose-Einstein condensates. So for cesium, the only stable isotope is a boson. And here we have very good vacuum conditions and long lifetimes in our optical traps. And here's a zoomed in picture of how the glass cell looks like, which you cannot see anymore. And here's a picture of the Bessel beam profile that we use for optical transport. So we have this running wave lattice geometry where we interfere a Gaussian laser beam and a Bessel beam. Okay, so the starting point typically for our experiments is to produce a BEC or degenerate Fermi gas. And we try to develop laser cooling techniques which allow us to reach this state as fast as possible and with as low temperatures as possible, because the temperatures that we reach here in the BEC or in the degenerate Fermi gas set essentially the lowest temperature that we can achieve for the following experiments. So starting from there, we will then load them into optical lattices and perform our measurements. Okay, so from this initial state, we adiabatically load them into periodic potentials, which we engineer by interfering, again, laser beams, now far detuned. So they are far off resonant with any internal transition. And making use of the AC-Stark effect, we can then generate these periodic potentials, which you also have heard of last week. So the characteristic length scale of this lattice is given by the wavelengths of the laser beams that we use to generate the potentials, which also allows us to do microscopy, which I will briefly introduce in a second. Now, the dynamics of atoms in these periodic structures can be described by Hubbard models, which, as far as I know, you also have heard already this week and last week. So they are basically, it's a very simple model. There are two important parameters. It's the hopping matrix element J that describes tunneling between neighboring sites. It's a real quantity. And then there's a Hubbard interaction energy U. When the atoms meet on the same site, they can interact. So that's the simplest model that we can write down for the dynamics of our atoms in these lattices. And despite this rather simple model, there are a lot of interesting and open questions. However, everything that I'm going to tell you is not really about the interesting properties of the Hubbard model. I'm trying to tell you how we can use new techniques, engineer new techniques in order to go beyond what we have already by just loading the atoms into this lattice. And then we can do a lot of interesting experiments, as you have also seen. Since these atoms are very nicely isolated from the environment, we can ask fundamental questions about thermalization. So you prepare your quantum system in a certain initial state and you watch it relax. You ask, does it reach thermal equilibrium even under unitary dynamics of the Hamiltonian, for example? So we can play around since basically we can tune all of these microscopic parameters dynamically by changing our intensity of the latest laser beams or using Feshbach resonances. So this allows us to do analog quantum simulation, where then the idea is that the atoms, the motion of the atoms in this periodic potential essentially resemble the motion of electrons in a real material. Of course, very, very much simplified. We get rid of phonons, we get rid of defects, we get rid of disorder, which then, if we are interested in studying these properties, we try to put them back in by hand, okay? And then the crystal, which is just engineered by the laser beams that we shine onto the atoms, resembles an iron crystal as you would have it in a real material. Now, of course, at very different length scales and energy scales. Okay, so if we, since basically the distance between neighboring atoms is rather large, if we talk about ultra-low temperatures, we are in the nanokelvin regime. But in condensed matter physics, since the distance is much, much smaller, and the Fermi energy is much larger, you can reach similar temperature scales, effective temperature scales, even if you cool down the samples to like millikelvin. So one has to compare the different energy scales of the two systems. So now, how can we do microscopy? So since the atoms are very far from each other, we can think about imaging them individually, something that you could not do with electrons in a real material. So this gives you a completely new access to observables and the physics of the system, because we can now try to take snapshots of this density distribution. Now, in our case, what we do is we essentially freeze the density distribution by ramping up a pinning lattice, which in our case is actually also the physics lattice where we study the dynamics, but we make it very deep, on the order of 100 microkelvin in depth, like each individual well in this lattice. And then the idea is that we can scatter a lot of photons while cooling at the same time in order to have like a steady state temperature that is like a tenth or even smaller than the depth of the lattice that we ramp up. So we shine in near resonant laser beams. So in our case, that's cooling beams detuned from the D2 line of cesium. And then we collect many, many photons, which could be like a few thousand photons per snapshot. And then really each individual atom fluoresces and shows up as a dot on our CCD camera. Now, because we have these very high resolution images, so here you see it has an NA of 0.8, we need to confine the atoms into a single plane, because otherwise, due to the depth of focus, it would completely smear out. So we are usually confined to 2D planes, and then we take snapshots of the atoms that are arranged in this 2D lattice structure. So this is the geometry that we have in our experiment. Here you see again the glass cell. We have a top port and a bottom port in order to have two high-resolution microscope objectives, one from the top and one from the bottom. And then we have vertical lattices that we shine in under an angle. They interfere, so they create these pancakes, and then we trap the atoms in a single node of this vertical optical lattice. And then these molasses beams that are also shine in from these angles and from the side, which we use to scatter photons. And then you get snapshots that look like this, where really each one of these dots is a single cesium atom that is trapped in this optical lattice and scatters a few thousand photons. So here we went to very low density, so you can count by hand, like how many atoms there are, you immediately see it. And then we can analyze how good our imaging works, so we can take histograms to evaluate the signal to noise. So here you see that you can very well distinguish if there's no atom or if there's one atom on a specific lattice site, which of course gets much harder if you have a higher density of atoms. So this is something that we are working on, because the point spread function, if you evaluate it for each individual atom, is, in this case, 830 nanometer. So in order to resolve the lattice constant, which is on the order of 380, we need to work a little bit harder in order to reconstruct the density. But the idea is that then in each experimental cycle, so what you have just seen, starting from the oven section, the CMOS slowing section, the mod cooling stage, evaporation in the glass cell, the transport in between, loading into the lattice, loading a single plane, taking a snapshot, will then give you one result of the density distribution. So you have your many-body wave function, you project it down onto one density snapshot, and then you repeat it all over again to get a lot of statistics, and in order to be able to measure then density-density correlation functions, for example. So what is also very important for us is that this whole cycle time that we need in order to get a single snapshot is as short as possible, such that we have a high rate of data in the end. Okay, so this gives us basically a unique tool set. This is nothing new. Many people use these techniques in the lab. Here we have now done it for cesium atoms. But then this is our starting point. So starting from here, we would like to study something interesting related to topology. And we have already heard a little bit about integer quantum Hall effect, which shows up at these quantized Hall plateaus in the transverse Hall resistance or in the connectivity. But there are many different topological phases of matter that would be interesting to study. I will mostly focus on this section up here, which gives a nice starting point in order to understand the techniques that we have developed in the lab in order to make the system topological. Okay, so let me remind you what the quantum Hall effect is about. So we have heard already these beautiful lectures on transport from Thierry, where, as you know, it's actually even in classical physics also not so easy to get this nice linear relation between the magnetic field that we apply and the transverse Hall resistance. But nonetheless, so this is the regime where in principle you could extract the charge carrier density from these measurements. But then it turns out that if you take a two-dimensional electron gas and you cool it to very low temperatures and you crank up the magnetic field that you apply, that then there are deviations from this linear curve. And there are these quantized Hall plateaus that appear. And if you look at it for the first time, maybe you say, well, okay, there are plateaus, so we can try to understand that. But what's really the fundamental new insight that we get from these plateaus? So first of all, these plateaus can be reproduced and measured very precisely in like 1 parts per million. And maybe you heard that it has been also used now, the von Klitzing constant in the redefinition of the SI units. So this is extremely precise, it works extremely well, and it does not depend very much on the geometry of the sample, like where you put the leads, where you put the contacts in order to perform the measurement, which is something that in condensed matter, as far as I know, I'm not a condensed matter physicist, but this is not something that you easily get. So usually if you prepare your sample, there's something that is different from time to time. The charge carrier density may be different, and the leads may be different, connections not so well. But here, these plateaus are extremely well reproduced and can be nicely compared even between different labs around the world. So very early on, it has been used already as a way to compare resistance measurements. And now, this is actually something I wanted to ask, but Thierry already told you the answer, I think. So the question is, why 2D? Like, the question was really, is 2D special for this measurement? Why not 3D? Why do I need a 2D electron gas in order to see this nice effect? But maybe you remember. So let me just briefly take one step back. So we have our quantum Hall bar, right? So it has different leads. It has this 4-terminal measurements. We send a current through the sample, and then we measure the transverse Hall conductance or Hall voltage in order to compute the transverse Hall resistance that is plotted here. But why does that work so well for 2D, which I think is one of the reasons why topological physics have been discovered in this geometry for the first time? I think I didn't tell you everything. That's maybe why you didn't recall what I want to say. But what we want to measure, or what is the quantized quantity here, is the resistivity and the conductivity. And in 2D, there's one-to-one correspondence between resistance and resistivity, which does not depend on the size of your Hall bar. You don't want to have a measurement where this depends very precisely on the length of your system, or maybe the area of your system, because otherwise you're screwed. If you want to measure something very precisely, measuring length is very hard. So this is actually why I think the 2D integer quantum Hall effect has been discovered in the lab earlier than maybe the 3D topological insulators that we now also know exist. Okay, so these plateaus are extremely interesting for technological applications, and in particular they depend only on natural constants, h and e, and integer quantities. And now the modern interpretation, although I have to say I think it was only shortly after the quantum Hall effect was discovered, but the interpretation is that this robustness of the plateau values depends on the topology of the energy bands that are occupied with electrons. So the idea is that if you think about the band structure of a material, then we know in this periodic crystal that they are confined to certain energy bands and there are band gaps. And now, just for now, accept that for each one of these energy bands, I can assign an integer quantity, a topological invariant, which is the so-called Chern number. And now, if I have my Fermi energy within a gap in the spectrum, I simply count all of these integer numbers of the bands that are occupied with electrons, and this will give me the value of the plateau of the Hall resistivity, the transverse Hall resistivity that I measure. And now the robustness comes in, that this is really an integer quantity that characterizes the energy band. So if there are small deformations, smooth deformations of this energy band, it does not really change this integer number that characterizes the global properties of the energy band. So this gives you a sense of where this robustness comes from. And then I will maybe at some point also talk a little bit about edge modes, but then there's this unique correspondence between the Chern number of the bands that we have in the system and the number of edge modes that we have at a topological interface at the edge of a quantum Hall bar, which is a topological interface between the Hall bar and vacuum. Okay, so the first task for today is actually taking a step back and just giving you some intuition about geometric properties and topology. And I want to introduce this in the following way. So this slide you may have seen already in some form or the other. But essentially what I want to say here is that the topological invariant that characterizes the energy bands can be understood in analogy to the classification of geometric objects, where the idea is the following. So you look at one of these objects, the surface of this torus, for example, and you characterize it by computing the local curvature of this manifold or this surface of the torus. And now if you integrate it over the whole manifold, the whole space, then you get out a quantity which can be related to, in this case, the genus of the object, which in this case is just a hole. So for the torus, you would get nu or g equal to 1, a genus of 1. For the cup, you would get a genus of 1. And for the sphere, you would get a genus of 0. Okay, so there's this correspondence between a quantity which locally tells you how the surface of the object is curved, how it varies in space. So there's a well-defined connection between two individual points on the surface. And then you can evaluate this integral, which gives you a global quantity that characterizes the properties of your object. And by just looking at this expression and accepting that this works, you can maybe get an intuition or understand why, if you now change this omega a little bit, so you deform the torus a little bit, you deform it into something that looks a bit more interesting other than just a symmetric ring, that this will not immediately change the genus of the object. It will not immediately change the integral of this quantity unless you do something a bit more violent like punching a hole through the sphere, then you change the genus from 0 to 1. And it turns out that this is a very nice intuition or picture in order to also understand the topological invariants that characterize energy bands. So here we don't live in real space, so we don't use the coordinates x, y, and z, but we use the quasi-momentum, which is the quantum number that we need for our translationally periodic systems. So in a 2D system, we have qx and qy, the quasi-momentum, and the manifold is determined by the Brillouin zone. So if we want to integrate over the complete manifold, then we integrate over the full first Brillouin zone, and then we can assign an integer number to each energy band, which is called the Chern number. And again, also there, if we vary or deform the Berry curvature a little bit, this will not immediately change the value of this integral, which is given by an integer. Instead, we have to do something a little bit more violent, and this violent thing that we would need to do, in, like here, punching a hole, in our case, means there is a spectral gap closing point. So if we have two bands that touch across the topological phase transition, these band touching points, they are sources or drains of these non-trivial geometric properties, so they can then lead to a change in the Chern number of the band. Okay, so this is basically to set the stage, what these 4 lectures are supposed to be about. But before we look into how interesting systems can be engineered with ultra-cold atoms, I want to start with a classical analogy in order to really give you an intuitive picture, an explanation of geometry and how this can lead to interesting effects. Any questions up to this point? Yeah?
Can you repeat why the Hall effect in the experiment was in 2D and not in 3D?
It wasn't, sorry?
In 2D or instead of 3D?
Yes, so the quantity that has topological protection or arises due to this non-trivial topological properties is the Hall resistivity. But what we measure is resistances. So you cannot measure like currents, voltages, and get a resistance out of it. We don't measure directly resistivity. And the relation between the two depends on the geometry of the system. So it scales with order L. So I think Thierry had this quantity in his lecture. So dimension 2 is special because then this dependence drops out. And there's a one-to-one correspondence between the resistance that you can actually measure and the resistivity. Yes, thank you. For 2 it doesn't matter, but for 1 it does. I live in 2D space, so it's okay. Okay, so what we want to understand are geometric properties or geometric phases. And the final goal for today is to understand geometric phases in quantum mechanics. And in particular, we do that for cyclic evolutions. This means we take some state psi at t equal to 0, and then we define some parameter space, which can be given by some abstract parameter r. It can be a vector, so there can be several different parameters that we can tune as a function of time. And then we explore this parameter space, but in the end, we come back to our original parameter set. And the question is, what is the state at the end of this cyclic evolution? And does this lead to interesting properties? Now, I'm taking something that I will tell you later, but just for now already, we will consider adiabatic evolution. That means we will in particular consider a system where initially we start in an eigenstate of a Hamiltonian, then we adiabatically move it in parameter space. And if we do that adiabatically, it means we will always remain let's say in the ground state, if we start in the ground state. So this state at the end of our closed loop has to be the same as the one that we started with, but there could be an additional phase, the geometric phase. So after capital T, we obtain our initial state again. This is what we will do after discussing the classical case. And the question is this phase non-trivial, and is it even interesting? But let's first talk about a concept that is known as parallel transport. And parallel transport is a concept that allows us to think of how two neighboring points in a parameter space are connected. Okay, so the concept of parallel transport allows us to define a quantity that connects neighboring points. It allows us to characterize the local curvature of some abstract manifold, which in this case would be given by the parameter set R. So we try to understand how this can be done and how this can lead to interesting effects. And for that, we don't need any quantum mechanics in order to understand that. So, and we can start with something simple. That is, we just live in 2D space. So for instance, on this board, just a flat sheet of paper. Then I can define parallel transport for a vector by just transporting it along a curve or a line, as shown here. And I define a certain set of rules. I say I don't want the direction of this vector to change, and I also want to keep its length constant. Okay, so I just transport this vector along this line. This is very simple, and in the end, I will find, okay, at this final point, it has the same direction and it has the same length. Nothing changed, because that's the set of rules that I defined for my parallel transport. And if I make a closed loop, it still looks the same. Okay, there's no rotation, there's nothing that happens. But now this concept can be generalized to something more interesting. That is, if we consider curved surfaces, like the surface of a sphere, for instance. But now we have to modify our set of rules a little bit and specify what we mean by parallel transport on the surface. So what we will say is that the vector is constrained to lie in the plane tangent to the surface. And the vector is not rotated around a normal that I define with respect to the surface. So this is my set of rules. And now I would need my screen, but let me try to draw and give you an idea of how that works. So let's consider a sphere where I try to apply this set of rules. Okay, so I start up here, and I take one section of this sphere. So let's say I choose this path that goes down to the equator, then I go over here, and then I go back up. So that's 1/4 of the top half of the sphere. And now you can try to apply this set of rules. Okay, so I have this little vector which I now want to parallel transport. And on each individual point, as I move it along, I define a tangent plane and I define my normal to the surface, to this tangent plane. So now if I do that and apply these concepts, it will first go down, it will go down, it will go down. It just follows because I've chosen it to be aligned with the direction that I'm moving down. Now when I'm down here, actually I have to move it like this. Okay, so it will follow along the equator. And then if I go back up, it will do this. Which means after I have performed a closed loop, there's a rotation associated with this concept of parallel transport. Where C now stands for the closed loop. Okay, so bear with me for a bit when I try to now formally define this parallel transport a bit more, and then you will see what are the implications of that and why it is interesting to define it in such a way, which already gives you an idea of how we are going to define a connection between separate points on a curved surface. Okay, so let's be a bit more formal. So we have this vector E1, which is this one here, which we want to parallel transport. And now we want to define the set of rules that allows us to do that. And our path C is parameterized by some vector R of t, which goes from t equal to 0 to capital T. N of R is our vector normal to the surface. And we'll define a second vector E2, which is orthogonal to both of them. So it's like a local coordinate system. Which also means that actually if E1 is parallel transported around the surface, the same will happen for E2 as well. Okay, so now we know that actually in this parallel transport scheme, E1, if it's parallel transported around on the surface, it will rotate. It will change its orientation because we have found that after a closed loop, there will be a rotation angle that it picks up. So they rotate with angular velocity omega. Which we haven't defined yet. Now, the formal form of our rules is that at all times, n dot ei is equal to 0. That's just a definition that we have used in the beginning. And we do not want that ei rotates around n. And this actually means that omega, our angular velocity, dot n vanishes. Okay, so that's one of the conditions that we apply for defining parallel transport. And now putting all of these together, you can try that yourself. So you try to write down the most general form for omega, which has components parallel to n, parallel to n dot, and then a third component perpendicular to n and n dot. Then you find that just by applying these conditions, we find that omega is n dot n cross n dot. That's just another way of putting into equations what we have said before and what we have tried out in this little example. And you can convince yourself that just by following these set of rules, you will actually find that this is the condition for omega that we need, which is now a formal definition of parallel transport. So now we can go back here. And plug this in. And now doing some algebraics, and using this condition, we can rewrite this expression as ei n dot n. Okay, so I'm almost done with all of these vector algebraics. And now we will express this in a slightly different form in order to connect to quantum mechanics later. So instead of having E1 and E2 as our unit vectors, we will introduce a complex unit vector E1 plus I E2. So we define this unit vector phi, which is E1 plus I E2 divided by square root of 2. So these are unit vectors, and we can already try to write it in a more suggestive quantum mechanical form by saying, okay, phi needs to be normalized. And now just using this expression that we have seen before, with the rules that we have defined, we can write it with our complex unit vector as phi star phi dot equal to 0. And we will see this expression later in the quantum mechanical form again, where we would have something like this, phi of t dt phi of t. And this follows from this expression and the set of rules that we have defined. Okay, so now we have found a definition for parallel transport, which also will appear again in the quantum mechanical version of it. Now, just thinking about this rotating coordinate space, we can also think about what it means to choose a different gauge. And we will come back to that, but in this vector picture, it is very easy to understand what we mean by that. So what have we done? We have taken these vectors that we parallel transport around the surface. So we have this orthonormal system, we have E1 and E2, and they move around the surface according to the set of rules that we have defined. But now there are many different choices that I can do. So I can define on each point on the surface a different coordinate system if I want, and call it t. Okay, so I can just define all of this rotation in some other reference frame. Now the only thing that I need to do is that this reference coordinate system is well defined on the whole surface, and it's smoothly defined. It shouldn't just jump like from one orientation to another. There should be a smooth definition of my reference coordinate system. And the equivalent of that in quantum mechanics will be our eigenstates. So in the end, when we describe the time evolution of our quantum mechanical state around this closed loop in parameter space, we express it in terms of our fixed coordinate system, which are the eigenstates, which also need to be smoothly defined within the parameter space. So again, there should be also a smooth connection of the phases, how it varies. There shouldn't be any jumps, which is actually something that will happen if you plug in some of these equations just in Mathematica to try to compute some geometric property. You will find that in general, Mathematica will not choose the smooth definition of the phase. So this is something to worry about. But let's stick with our easy vectorial representation for now. So we just assume this orthonormal reference system, which I call T. Okay, so now we have this vector n of r, This is uniquely defined. It's normal to our surface, so there's no gauge freedom here. And then we have a T1 and T2. So for a specific choice, I have my local unit vector that defines, now again complex, that defines my reference coordinate system. Which is fixed and a smooth function of R. And because we have chosen to work in this complex representation, the relation between my original vectors E1 and E2 and my fixed reference frame is given by just a phase, a rotation in the 2D plane. So this angle theta uniquely defines on each position in a parameter space what's the relative orientation between the two coordinate systems that I choose. Okay, so now let's look at our definition of parallel transport. Which looks very simple. It's just this expression. Okay, so we have phi star, phi dot. And now I just plug in this relation, which tells me something about the gauge dependence of the different quantities that we have introduced. Okay, so I just calculate according to the definition of parallel transport. This is 1 by definition. And this has to vanish. So now I see two things. So the first one is that this quantity has to be imaginary, because this is purely imaginary. And I get an equation for the time dependence of this angle. Okay, so what have we done? Basically, we have defined the set of rules for parallel transport in order to be able to compare the connection between different points on the surface. And we have decided to describe this transport in a fixed reference frame that we decided, this T1 and T2, where there are infinitely many different choices on how to do that. And now we can compute this angle theta after a closed loop on the surface of the sphere. Okay, so let's look more closely at this quantity. And use this in order to define a connection between neighboring points on the surface. So we define a vector field A as the imaginary of U star dx U. Okay, so now you may ask why, yeah.
I'm sorry, but I'm confused. What is theta of t, where it comes from? Because you have this imperative is this phase times this u, but where does this phase
Yes, I think for now it all seems very arbitrary, probably, because I have introduced all these different quantities and you may wonder, okay, well, so what? Now we have done this parallel transport, we have moved these vectors E1 and E2 around, and then we have made this arbitrary choice, which we describe by this angle theta, and now I ask you to evaluate it after a closed loop. Okay, fine. But what we will see is that this connection that we have defined here, which appears in the integral, for this closed loop integral, this arbitrary choice drops out. So we will find that this is a uniquely defined quantity which has a physical realization. So let me continue for a second, and then maybe we can discuss further.
Is there a necessity to carry that imaginary? Because like the equation star, I think it implies that you started up is imaginary. So why do we need to carry the imaginary?
Because then the phase is real in the end. So we just want to get rid of I. So different ways of defining it. So also sometimes you see that it's defined as I, and then the connection, at least in quantum mechanics, typically you have an I in front, just in the end of a real quantity. This you get out of here, right? So there's another I here.
So but that.
Okay, so now let's see what happens if you just make a different choice. And then we are almost done with all these vector gymnastics. So we get a new reference frame or new unit vectors. And if you use this definition and plug it into the connection that we defined, it changes. So A I prime will not be the same as the original one, which makes sense. Because I've completely changed my reference system that I use in order to describe what happens along the path. So of course, if this is my connection that tells me how two different points are connected on the surface, if I choose my reference system, it will modify the connection that we find. Okay, so in general, this quantity will depend on the choice of my reference coordinate system. But if we look at this closed loop integral, it will not depend on it. And it's because the closed loop integral over the gradient of this rotation that I've introduced up here vanishes. And the reason for that is that I always need to find a unique representation of my reference system. So for each point on the surface, they need to be uniquely defined and smoothly connected. So from my initial point and my starting point, the relative orientation between the coordinate systems is fixed. There's no freedom of choice. It's like for the wave function that I have a smooth definition of the phase, which is also called single valuedness of the phase. You want that the phase of the state that you're looking at is well defined everywhere along the path. And if you connect it to the original point, it needs to have the same value of the phase up to an integer multiple of 2 pi. Okay, so why am I telling you all of this? So the basic takeaway message is that we have defined, or we have found a way to describe connection between different points in our parameter space, which is the surface. We have found a definition for this connection, which, however, does not seem to be very useful because it depends on my reference coordinate system. Nonetheless, if I perform an integral over a closed loop, I get out a quantity which is uniquely defined. It does not depend on the local choice I made for my reference system. And it knows something about the geometry of the object. Like the quantity that I will get out here will depend on if it is a surface or some other manifold. And this is what we are looking for. We are looking for quantities that are gauge invariant and tell us something about the geometric structure of the manifold that we are interested in, which in our case will be the energy bands that live in Qx, Qy space. Okay, so if we go back to our example that we have started with, you can show that this angle that appears when you do this parallel transport with a vector quantity on a curved surface, like the sphere here, that this angle the vector rotates about, which here was 90 degrees, that's not a coincidence. You can show that this rotation angle is given by half of the solid angle that you trace out on the surface of the sphere. So this is a very powerful concept that allows you to compute such quantities where you ask the question, if you transport a vector quantity, and this can be now anything. A vector quantity could be the polarization of a photon or something else. That if you trace out such a parameter space in your manifold, like the sphere, you can find these simple quantities where you can show that this angle it rotates around is half the solid angle that you trace out. Okay, so let me give you 2 examples where this actually shows up in a physical system. Yeah.
So here you gave an example in 3D, like
Yeah.
a geometrical example in 3D. Was this the simplest? I mean, is there nothing appearing like anything like that in a plane? Like I don't know.
I think we will get back to that, or the solid state equivalent of a plane, which would be integrating along a line, as I've shown in the beginning, where parallel transport along a line is trivial. It's a bit more complicated, but I think I will get to that for the solid state example. So there are interesting effects also for flat spaces. Well, it's actually not flat; it's still curved. So I'm not sure. Okay, maybe we can discuss about this when I go to this example in solid state. But generally, I think in order to have something non-trivial, you need something curved, and then I don't know if there's anything in flat space. Okay, so the most well-known example, probably where these geometric phases show up, is Foucault's pendulum. Okay, so now after all these vector gymnastics, you can derive some very simple equation in order to understand what's the rotation angle of the plane of Foucault's pendulum if it traces out different loops on Earth. And basically what you find that this is simply governed by the latitude. So depending on if the Foucault's pendulum traces out a loop here or on the equator, it will rotate around a different angle. And this is given by sine of the latitude, which also means that if you are at the equator, nothing happens. And this you can simply understand by the concept of parallel transport that we just went through. But this, as I mentioned, generally happens for any vector quantity, so also for the polarization of photons. And I think the first measurement where people have reported a measurement of the Berry's phase, I didn't explain yet what a Berry's phase is, and the topological or geometric properties, was indeed with linearly polarized photons that propagate in a waveguide. So here, maybe the question is what defines the closed loop? So we have here a helium neon laser. There's a polarizer, then the photons are linearly polarized. They propagate through this fiber, and it's wound around a solenoid. And then performing a closed loop means that the k, the wave vector of the photons at the entrance, has the same orientation as the ones at the axis. So you can actually shrink this thing to a circle if you squeeze it together. And the rotation of polarization of the photons at the output is a geometric quantity that only depends on a more abstract half-solid angle, but it's very similar to what we have seen on the sphere. And again, what they have tried to do, which you can easily do in this fiber setting, is to vary the shape of the fiber, like how it is put around the solenoid, while keeping the solid angle constant for these measurements. And this was their first, I think, signature of showing that this is a geometric property, which really does not depend on the path, on the specific path that you're choosing, that is traced out, but that it only depends on half the solid angle that is subtended below the curve that you trace out. So here, that's actually on the horizontal axis, there's the solid angle. On the vertical axis, you see the rotation of the polarization that they measured. And they have chosen a certain setting for the fiber as it is put around. And then these open squares, and I think there are also some triangles here, they have measured by choosing a different setting and then always computing only the solid angle to see that actually indeed the rotation that they get only depends on the solid angle and nothing else. Like you can bend the fiber around, you can do whatever you want. In the end, it's just the solid angle that counts in order to define this rotation of polarization that you can see in the experiment. Okay, so bottom line, what I wanted to tell you is that there are powerful geometric concepts that allow you to learn something about the geometry of the space that you are living in, and it allows you to compute physical quantities such as that, which do not depend on the gauge choice, although the way that the connection is defined, and this is the same in quantum mechanics, we will also see how the connection is defined in quantum mechanics, heavily depends on how you define your eigenstates. You can still get out gauge invariant quantities. Okay, so now that's all about classical physics, and we'll move to quantum mechanics. Any questions? Yeah.
Okay, I mean this is quite abstract, right? But a way to understand this T that you were talking about is that if you have a gauge theory, right, you can always you have some physical configuration which is described by psi, but you can also always put on a phase to it and describe the same physical configuration.
Right.
But then in a specific gauge, then you trace out a path in the parameter space.
Right.
And then theta is the phase you pick up.
Right.
In the parameter space. So
right.
Kind of, the gauge is kind of whatever in a specific gauge the phases are somehow connected to this gauge.
Yes, that's precisely true. So again, if we go back to our example that we are interested in looking at something like this, so we have our initial state psi 0, and now we make a specific choice and we want to describe how does my state psi vary in the parameter space. So I can look, for instance, here. I can ask, okay, what is psi of t at this point? And I can always multiply some arbitrary phase to it. This just depends on how I want to define my, in this case, coordinate system. In our case, it would be how I define my eigenstates or my basis in order to describe this state. But now the point is that after I've performed a closed loop, so let's say psi of capital T, the system returns to its original state, but it picks up a phase which depends on the parameter loop that I trace out, and it cannot be gauged away. There's a phase that I get out of this calculation. Now, what's the implication of this phase? That's another question. But I can do that. I can do this calculation, and this phase really exists. And of course, in the beginning, I think it was way before my time, but when people started to discuss about that, of course, the first thing that you say is, well, who cares? If I now compute some expectation value of any operator A, I mean, okay, fine, there's a phase, but it drops out, right? So you don't care. And we will see that there are many examples where this phase plays an important role, in particular in the quantum Hall effect. Other questions? And let me put this classical expression here, maybe, because we will find it again. Or the so-called Berry phase. Okay, so let's define what the Berry phase is. So now we work with a Hamiltonian in some parameter space R. Which could be anything. And now for each value of R, we can define or compute the eigenvalues and eigenstates. These are our instantaneous eigenstates of the system. And here, again, I have this arbitrary gauge choice. So I can write down my eigenstates choosing a certain basis or a certain convention of the different phases. And I require that there is a smooth definition in the parameter space that I'm interested in. And as we will see, this cannot always be done for the full parameter space. Sometimes it's restricted to certain sections because there are singularities that appear. So if we compute the quantities such as the Berry phase or the geometric phase, it should be smooth within the region of interest where we perform the calculation. And now we look at adiabatic cyclic evolution. Where at any point on our loop, we are in an eigenstate of this Hamiltonian H of R. And adiabatic means that the rate with which we change the Hamiltonian by changing this external parameter is small enough, small compared to the energy gap between the different states, so that we don't generate any excitations as we vary along the path. So now I sketch Berry's derivation here. So psi at t equal to 0 is equal to n, our eigenstate, at the start of the loop. And now after time t, we can make an ansatz for our wave function, psi of t. Now, because we are moving in this parameter space R, of course the energy landscape varies. Okay, so there will be something like a dynamical phase just because we change the eigenenergy of the instantaneous eigenstate as we vary across the loop. So this we can already take out. That's not the quantity that we are interested in. And now this phi n is an auxiliary wave function which will be an instantaneous eigenstate at the position where we look and some potential phase factor, which will be the geometric phase that we want to compute. Okay, so let's use the time-dependent Schrödinger equation to compute what this phase is. So we project onto psi of t. To find the following equation. And now we plug in the ansatz for our wave function that we have defined here. So since we have imposed that we do this adiabatic, at any time t, we are in an eigenstate. So from applying the Hamiltonian h to our state, we just get the eigenenergy E minus IH bar, and now we take the time derivative of this expression here where we get two contributions. So this term we just get from this phase factor, the dynamical phase, which we put in there because we already know that according to the time-dependent Schrödinger equation, there needs to be this dynamical phase. So these two will actually cancel each other. And then we have another term which needs to be equal to 0 because these two cancel each other. And this is the quantum mechanical version of the parallel transport, if you wish. And from this, we can compute what's the value of the geometric phase that we get after tracing out such a loop. And now we do the same as before. In the classical case, we express this in the reference system that we already defined. So in our case, that's the eigenstates n In the previous case, it was the orientation of the local coordinate system. So there can only be a phase, which now is called gamma, and this is the equivalent of this angle theta that we have seen before. And now, in analogy to what I've shown you before, this gamma n dot is given by the imaginary part of n of r of t dt n of r of t. Which you can already see is gauge dependent. It depends on the choice of my eigenstates that I have defined. And so my state after tracing out a closed loop can be expressed in the following general form. So it has two contributions to the phase, delta n and gamma n, psi of 0. So psi of 0 is my starting point when tracing out the loop. And I get two contributions to the phase. The first one, which is the dynamical phase, and the second contribution, which is a geometric phase. And this is the so-called Berry phase. And what you can see is that it only depends on r. Okay, so there's no dr dt, like rate of change or the velocity with which you go through the path or anything like that. It only depends on how you parameterize the loop, like what's the topology of the loop or the winding number of the loop with which you take in order to perform it. And we have a Berry connection, similar to what we had before, that defines how these eigenstates vary in parameter space, which is our vector field A. So this thing is gauge dependent. And we have the Berry phase, which is gauge independent. So while if we again stop the loop at any point here, the phase that we arbitrarily multiply to our state can always be removed by a gauge transformation. I can always cook up a suitable choice of a gauge transformation that will get rid of it. This is not the case after the closed loop. So there's no way that I can get rid of this geometric phase or Berry phase gamma n. And the reason for that is that, again, for this choice of the eigenstates that I need to make, they need to be smoothly defined in the parameter space, and the states need to be single valued. I cannot just make a jump of the phase in my definition and introducing a jump here between the start and end position of the loop. Yeah.
Excuse me, I'm a bit lost with the notation. So could you repeat what's the difference between the states psi, phi, n, and n?
Yes, so n are the eigenstates, instantaneous eigenstates of the Hamiltonian. So we have this Hamiltonian h of r. It depends on the set of parameters, and that could be anything. But for each point along this loop, I can compute the eigenstates and the eigenvalues. And this is the choice I made then, which has the smooth phase variation across the whole parameter space. And then psi was used as a notation to describe the time evolution, which generally also involves additional phases. So in the spaces, reference spaces n, I could multiply an additional global phase to it if I want. So psi is the notation just used in order to compute the evolution. And then for this auxiliary wave function, phi here, it's called phi because although the system is in an eigenstate n, there is an additional phase multiplied to it. So that's why it's phi n to reference to the eigenstate n, but having the freedom of an additional phase that we compute during the evolution. Yeah.
So like when we write phi n equal some phase to the eigenstate, it's just an assumption, let's say. It's not something to derive.
Yes, so at this point, when I write that, I'm just saying that there can be a geometric phase. I haven't computed it yet. But in general, there could be an additional term. And if you go through the derivation using the time-dependent Schrödinger equation, you will find that indeed there's this geometric phase, which I can then compute. Where did I write it? According to this. So the geometric phase I can indeed compute by looking on how the eigenstates vary as a function of this parameter r in my parameter space. Which remarkably, after a closed loop, does not depend on my choice anymore. It has a real physical meaning to compute this Berry phase. And I had 2 examples for you where these Berry phases show up, which I will then do next time. Maybe just as a teaser for you to think about. The prime example is a spin 1/2 in a magnetic field, where the magnetic field depends on time and can rotate. And the second one is the Aharonov-Bohm phase that we will also have a look at. Okay, so if there are no more questions, thanks, and see you tomorrow. Well, we'll see you later.